Connection design. So this example is a steering suspension system and the steering knuckle connection. So this is the strut that where's my pen? So that's the strut that gets connected. This part, the strut plate, is connected to the steering knuckle. Now you can see this here. This is the strut piece right here, the plate and the bolt connection, and this gets connected to this steering knuckle right here. So the type of failure you can have in this case, this strut bolt might get sheared off. So if the bolt is weaker, so number one, it can fail because of the weak bolts. So bolt is sheared off by the plate. Number two could be maybe the bolt is strong, but these strut plates may be sheared off, cut off by the bolt. Same thing for the steering knuckle, that could be cut off by the bolt. So that could be the the plate, connecting plate failures. So weak plates, it could fail because of that. Either steering wheel knuckle or the strut plate, either could go fail. And number three, the final type of failure could be because you are cutting a hole there, this place is weak, so it might not get, so there is a force going upward, so it might not get, just it probably not be able to take the tensile load, so it might just crack here and fail because of not able to take the tensile load that comes on this connection. So these are the three types of failure we can have. Now this is very simple. We're just gonna calculate these three steps. So let me show it here. So step number one is to check for the weak bolt. So imagine that the bolts are going to fail. They're not strong enough to hold this connection. So if you think about, draw this strut bolt, let me draw it. So this is the bolt. Imagine that it kind of cuts off right here. So right here it cuts off there. So all we need to do is how much force do we need to make this cut like this right here on this bolt. So to find that force, we know that force or load, in this case amount of force we need, or load, allowable load applied to this bolt is the, so if we want to calculate the allowable force or stress for which this bolt will be okay, so the allowable load on this bolt is the allowable stress times the area. So then the allowable stress for the bolt material, assume that this can be found from any textbook. We are using a 325 bolt. Or A36, any type of bolt. So you can get this material property for A36 is 34 ksi. Bolt material allowable stress, allowable shear stress, the maximum shear stress for A36 type of bolts, if it designed by that kind of bolt material, then 34 ksi times the bolt diameter, because bolt area, because this is the area, the cross section area of the bolt we are cutting, which is pi by 4 d square. This bolt, it says 5 by 8. You can go back to the video and check the bolt diameter. So 5 by 8 inch whole square. Now look at this situation. You got two sets of bolt here, two bolt, one bolt here, one bolt here, and this bolt is sharing at two planes, right, on this upper here and then lower here. So you got two. So then with these you are multiply by the number of bolts and then multiply by the number of planes, shear planes. that this plate has to cut. So in this case you got 2 bolts, 2 shear planes. I have calculated this 41.7 thousand pounds allowable for the bolt. So this is the allowable stress, allowable load for these bolts. So this is the maximum these bolts can take. So in the end we're gonna see all of these allowable max and then find out how much maximum this connection can take. Now let's check. Step number 2 is to check for the plate failure. Assume that I got these plates are weak. So here I got 2 plates. One is 2 strut plates and knuckle plates. So for these strut plates, if I just look at this strut plate, let's look at it vertically. So it looks something like this. If I draw this strut plate, I'm just draw one of the plate right here. So just maybe the top plate, and I got 2 holes here. So I'm trying to calculate how much allowable we can have for this plate. So imagine that you're moving your finger on inside jello. So this plate is bolt is going to shear off like this. So how much? So it's going to just cut this plate this way. This will cut this plate that way. So we can write that allowable force formula. So allowable force or load for the plate would be allowable stress for the plate. Allowable stress times the area that cut by the bolt. So the area cut by the bolt times the number of bolts. If you move more fingers in a jello, it's gonna be more difficult. So number of bolts, and of course times the number of plate. So if you have to move 2 different cut 2 different plates, in this case for the strut plates there are 2 plates, so it's gonna cut 2 plates. So you have to consider that as well. So for the strut plate, let's assume that the strut plates are made of A36 carbon steel. So for the A36 carbon steel, the allowable stress given is 87 KSI. So I can plug all this number, 87 KSI allowable stress times the area, which is 5 by 8, the thickness of the bolt times the diameter of the bolt times the thickness of the plate. This is the amount of material cut by the bolt times the stress times the number of bolts times the number of plates. So I have found that 27.2 thousand pounds. So these strut plates can take this much. So this is the allowable load for the strut plate. Allowable load for the strut plate, 27,000 pounds, and allowable load for the bolt is 41,000 pounds. Let's calculate the steering knuckle load. So for the steering knuckle, we are still on step number 2, just checking for weak plate. However, in this case I got 2 sets of plates, the knuckles and 2 types of plates and the strut plates. So for the knuckle, same formula, we are calculating the allowable load that can be taken by the knuckle, steering knuckle. So the knuckle load, basically allowable stress times the area times the number of, basically this area is cut by the bolt, area cut by the bolt, because we are assuming that bolt is stronger in this case and plate weak plates cut by the bolts, and then the number of bolts and then the number of planes that this cutting. Now steering wheel just one plane, so that's gonna be 1 for steering wheel. In this case, the steering wheel knuckle, they are actually made typically by gray cast iron. So they are not your typical connection materials. For cast iron, the ultimate shear stress is 32 ksi. So that's not in the connection design table. This is from the material properties table. So 32 ksi ultimate strength. So I'm going to use that for this design. So 32 ksi, that's the maximum cast iron can take shear stress wise. And then the area cut by the bolt is the bolt diameter 5 by 8 times the plate thickness. The plate thickness is 1.3. You can go back to the problem and read the knuckle thickness. Times I got 2 bolts, so 2 bolts are cutting this knuckle, and then just only 1 knuckle plate. And I have got 52,000 pounds for the knuckle plate. So the allowable load for the knuckle, the allowable maximum we can allow for the steering wheel knuckle is 52,000 pounds, which is huge for a small car. Now step number 3 is the tensile failure. Tensile failure. So what could happen is, if you think about this plate like this, and you are cutting 2 holes here, so it's gonna be weaker here, so it might get cracked under tensile loading. Now on the steering wheel knuckle and suspension cases, it's not a huge tension that this thing goes. However, it might also fail this way. Let me calculate that. So for the plate, if we think about the plate, just simply calculate the allowable tensile stress. So allowable tensile stress basically is the force divided by the projected area. So this is the area we are talking about. Now for the plate, this is 2 inches. You can go back to the book and go back to the problem and read it. So 2 inch by the thickness, which is 1.8. So if we calculate the allowable stress, allowable tensile load, that's going to be the allowable stress, which is for A36 carbon steel type of plate, which is given 29 ksi. Yeah, I think that's it. Yes, so that's 29 ksi. You can find that from the table. 29 ksi times the area, which is now 1.3 times 1 by 8 minus the bolt area. So that's not gonna carry anything, so you're gonna subtract that. So if I calculate this, I found 4.9 thousand pounds, which is probably very, very low. However, it will not go under too much tension. Now let's calculate the this is still step number 3. However, we're going to calculate for the knuckle tensile stress failure. So same thing, allowable for the knuckle tensile stress. Now knuckle made of gray cast iron. So for gray cast iron, the tensile ultimate is 20 ksi times the area of the knuckle, which is 1.2 times 1.3 minus the bolt area, because that's not going to carry anything. You got this hole there, that, so I calculated that 16.2 thousand pounds. So to review, your answer will be the lowest number for these connections. If somebody asks you that what is the maximum this connection take, you can say about 5,000 pounds, because it's gonna fail if it goes under tensile load. However, remember this this might go different types of loading, so you should always point out this, that the tensile loading, it can take maximum 5,000 pounds. For this knuckle, it will take 16.2 thousand pounds, because knuckle is made of out of a different material than the strut plates. So, and also you can point this, the maximum that bolt can take is 41.7, maximum the plate can take is 27, and so on. So you report all of these. However, if somebody asks you what's the maximum this connection can take, your answer will be this minimum value 4.9.